Hi, bit of a short video today. We're going to look at just a couple of different ways to look at these molecules when we put them onto paper, really. So as a do now, just to get a reminder of where we were in our last lesson, here is a sample molecule. I need to correct something I said in my last video, which is why I chose this one. But just take a few minutes and try and fill out the 3 prompts that are there. Hit pause because I'm going to start soon. All right, good. So the big error I made is that it turns out that 2 times 10 is in fact 20. And I mislabeled this compound. So this would fit into the CnH2n-2 category. So these are alkynes. This specific one is called decyne. Oh, I just screwed up. I'm going to have to fix that later. It's okay. We'll fix it when we get there. And then if I were to draw a Lewis structure, well, you might have drawn a couple Lewis structures, but I think 2, 3, 4, 5, 6, 7, 9. This would be one that would show up most frequently. And this is where you're really going to make sure you did things correctly, because when you count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17, 18. And that's, keep in mind that you don't go over 4 bonds to any one carbon. So that would be one that you may have drawn. But this is a lot to draw. Now, if you drew something that isn't this, we're going to talk about that in a few slides. Very important concept. But before we do that, we have to talk a bit about how we represent these on paper, like I said. What I just drew is what we would call a structural formula. All atoms, all bonds. So I can copy that below, again, forgive me. And as a reminder, don't forget, every line that doesn't have something drawn on it on one end, it's assumed that there's an H there. But this would be the structural formula of this compound, decyne. The molecular formula is just each element and number. So you've seen molecular formulas when we talked about molecular and empirical formulas. So the molecular formula for this compound would be C10H18. So both of these we have some familiarity with. The structural formula is like a Lewis structure, except usually we don't worry too much about the lone pairs. And the condensed structure is actually somewhere in the middle. To write a condensed structure, this works out really nicely if you want to type something into a Word document, like write it out on paper, so you don't have to draw the whole thing, but you're communicating some of the structure so that someone reading it can figure out what it is. Label each carbon and what's attached separately. And I'm going to show you what I mean with this one. So basically, we're going to write each carbon separately. So instead of C10, you're going to see 10 Cs in your compound. After each carbon, you list the elements, the atoms that are attached just to that carbon. So for example, to start this off, it would be CH, right? There's one H attached to that first carbon. Then I would write C. And then there's nothing else attached to this that isn't already another carbon. And then after that would be CH2. CH2. I'm going to keep track so I don't do this wrong. CH2, 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 CH2. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the last one is actually CH3. Squeeze that in there. The idea being now, if you were to look at that written out on paper, you would have a little bit more of an idea of how this molecule is built, without me having to actually draw like sticks and lines on a piece of paper. I like condensed structures for people who are like typing things up. It's a way of communicating, but you can see that it's a lot longer than just listing the molecular formula. What I do see sometimes is that people will abbreviate by doing things like this. 2, 3, 4, 5, 6, 7, 8. No, 1, 2, 3, 4, 5, 6, 7. That's what I thought. You might see something that looks like this. This is like taking condensed to another level, but it kind of fits into your condensed formula. So the one thing I want to talk about is if you had drawn this, and I'll draw those in a little bit clearer because they look a little blurry on the slide. If you'd drawn that for your structure, oh, I gotta erase more things. This shouldn't be there either. There we go. Now that's Dekine. I got a picture of Dekine by mistake. If you had drawn something that looks like this, though, 4, 5, 6, 7, 8, 9, 10. If that's what you had drawn when you hit the pause button and drew out C10H18, you wouldn't have been wrong. If we count things up, there are 10 carbons and 3, 5, 7, 9, 11, 13, 15, 18. There are 18 hydrogens. The problem is that these two chemicals are different chemicals. They have different properties. So I would say what's different is the structural formula and the condensed. Obviously, if we were to write out the condensed formula, this would be CH3, CC, CH2, 6, CH3. So that's different than the one that was CHC, CH2, 7, CH3, right? So like but if you do mush them together all the way, here we get C10, H18, and here we get C10, H18. So what they have in common is your molecular formula. And so we have a name for these compounds because these compounds usually do have different properties, but they're very similar to each other. Isomers, same, I believe mer means like unit, same unit. It's same molecular formula, so it's the same atoms all put together. They're just put together in a different way. A third way, if not to get too pointed with it, a third way to draw this would be to do something like this. 5, 6, 8, 9. And then when you put in these, and to put something on like a side or a branch, this is still C10H18, so this is still an isomer. So when you get these bigger organic hydrocarbons, the number of isomers that you can make goes up dramatically. But hopefully you did just draw one of the linear ones. You maybe could have put the triple bond in the middle or, in the quarter or something like that. And we're going to talk about those next. But just to give you a bit of more of a framework for detecting these isomers, the one thing we have to think about with organic chemistry, do you think that these two substances are isomers of each other? And the question is, do they have the same molecular formula but different structural formulas? And to look at it, it looks like they're kind of different, right? Except not really. You have to remember these molecules flop, twist, and turn. So like if you had something like this butane substance, and then you had something that you drew like this is still butane. They're all attached the same way. We built it the same way. Just because some things have twisted or turned, these are not isomers at all. They're the same molecule. For something to be an isomer, it has to actually be built in a different way. So usually the way I think about it is when you're making an isomer of a compound, you actually have to like break and make a bond. Rearrange how they're connected. Don't just spin the molecule or flip the molecule. You can't do that. That doesn't work. So just to summarize things really quickly, here's a table. Like I said, nice and short today. I want you to hit the pause button, maybe go to your notebook because it might help for the structural formula. For each row, we're all referring to the same substance. So C2H6, I want the condensed formula and the structural formula. My suggestion might be to get the structural and the molecular ones settled first, and then go back to the condensed, because for me, writing a condensed from a structural is easier than going the other way. But like I said, hit the pause button if you need some time. I'll finish my drink. But I'm going to get started. So I don't really, we're just going to there's only one way to draw this. If you have 2 carbons and 6 hydrogens, there's actually no way, given that hydrogen only bonds once, to draw this. So our condensed formula would be CH3, CH3. For this one, it's a little bit hard to write the structural formula, but I am going to come over here and I'm going to write the molecular formula first. I count 4 carbons and 10 hydrogens, but I know I need to draw a CH3, and connected to the CH3 is a CH, and then it says CH3, and I can't put another C here because there's already an H. So for like this one, maybe I should fill this in. I think this CH3 is actually attached to this carbon, and this CH3 is actually also attached to this carbon. For me, this is actually a nice way to see this. When I see multiple CH3s in one condensed formula, that tells me that there's actually going to be a branch on my hydrocarbon. There's going to be some point where there's like not just a straight line, but there's this branch. So we said acyclic linear. These are acyclic branched instead of just the acyclic linear. Both of these together, I believe, are called aliphatic hydrocarbons, branched and linear. But just so you know, that one, we're not going to name that. This is ethane. This one looks like butane. And this one we're going to save for next time. But we can turn this into a condensed formula, CH3, CH2, CH2, CH3. And then if we add them up, actually, we get C4H10. So these are isomers of each other. See, they're both C4H10, but they're clearly built different ways. We have 4 in a line and then 3 in a line with this little thingy on top of it. Notice when you look at the condensed formulas, you can see it very clearly. There's a difference in how the atoms are put together. Instead of CH3CH, CH3, CH3, it's CH3, CH2, CH2. It's like you literally moved an H over. So what's kind of cool is we really get, hopefully you have a good way of picturing these in your mind, because you really get a lot out of this once you can kind of picture them and flop them around and spin them in your head. Thanks for watching.